this lesson, we'll discuss the theoretical underpinnings behind the regression algorithm. We'll start the discussion with the background and motivation to regression modeling technique. Next, we'll discuss the types of data employed in the regression modeling. We'll also discuss in great detail the cost function, that is ordinary least square method, which is widely employed to fit the regression line. Next, we'll discuss the simple and multiple regression modeling techniques. Next, we'll examine the key assumptions behind the classical linear regression model and implications if these assumptions are violated. We'll also discuss the BLUE, that is best linear unbiased estimator properties associated with the OLS estimators. Lastly, we'll briefly cover the role of normal distribution in hypothesis testing associated with regression modeling. We'll also discuss some non-linear functional forms that can be suitably modified to linear functional forms. In this video, we'll provide the background and motivation for the application of machine learning algorithms in business applications. Many times on Amazon and Netflix, we get recommendations for movies and TV series as if some human person has examined and carefully vetted our history of TV or movie watching and provided these recommendations. They are extremely accurate. Also, you would have observed the spam filtering application on your mobile text messages and email applications. If you carefully examine these filtered messages, you would find almost 95% to 99% accurate messages and emails that are like phishing emails or bulk mails which are targeted to bulk audience and not very genuine mails or messages. Also, if you go to website like Google News, you will find news items clustered and put together in groups as if somebody has carefully read these news items and put together similar news items, putting together these news items for our ease of reading. To summarize this discussion, in modern day business applications, for example, Amazon and Netflix movie recommendations, filtering out spams, medical prognosis based on previous health records, algorithmic trading, credit scoring models, these applications appear or are driven by computers without being explicitly programmed. So here computers are learning without being explicitly programmed, for example, in recognizing handwriting, natural language processing, and so many applications in modern day-to-day and business applications where computers are acting as if some human being is working behind the curtains. But obviously, given the volume and nature of data, big data being handled, a human being cannot do these things on their own, and therefore we clearly understand that these are computers working behind the scenes without being explicitly programmed. They are made to learn through these machine learning algorithms. In this video, we'll provide a brief background to machine learning algorithms employed in business applications and finance. Let us start with a very interesting supervised learning problem. In supervised learning, we have a set of input features which are mapped to output labels. Now please note the important keyword here is that output is labeled. So a set of features, input features and output which is labeled. The algorithm is trained using this input output data, and once the algorithm is trained, it is employed in future using these input variables or features to predict the output. A very simple example to this is house price prediction problem, where a set of data, that is size of house in square feet, which is one of the features, and the label, that is house price, is given, and using this data the algorithm is trained. This is called regression problem, where we try to model this using regression. In this lesson we'll discuss the regression problem in great detail, but as a simple example, using this feature which is the size and output label which is the house price, the regression model or algorithm is developed, trained, and for future when the size of a house is given, the algorithm is employed to predict its price. Let's say some new points are given, then this algorithm will predict their price by fitting a regression line, which we'll discuss in detail in this lesson. Another interesting supervised learning problem is classification problem, where a certain label data is given along with features, and then algorithm is trained to classify the new observations across these labels. For example, credit default scoring problem, where we try to classify observations such as loan applications into defaulters. For example, here defaulters are given in red and non-defaulters or good credit borrowers are given in blue. Now we have two features. The labels are defaulter and non-defaulters, while features are net worth and income. Now using the given set of data, we train this algorithm. And once we have the algorithm trained, then as the new data comes in, for example, new data maybe here, using this classification problem, we try to classify the new observations into defaulter versus non-defaulter. Using this model, we try to predict that. We try to classify or segregate defaulters vis-a-vis non-defaulters using the algorithm that has been trained. In the unsupervised learning, the key difference is that the data is not labeled, we have only features. For example, you may have demographic variables such as taste, income, age, and gender. And based on these features, you will try to segregate individuals into different groups. And this is a very useful application in market segmentation by consulting firms who employ such data in creating target segments for targeting them for their products. Such segments are based on this clustering problem, where we try to cluster individuals based on certain features such as taste, income, gender, and so on. So this is a very interesting business problem, clustering problem of market segmentation. Another very interesting clustering problem that we already discussed is clustering of news items depending upon their similarity. So natural language processing and text processing, text analytics applications and algorithms are employed to segregate news items into clusters that are similar based on certain features, maybe genre of news or similarity in terms of geography or the topic of news. They are clustered together by unsupervised learning algorithms that cluster these news items together. To summarize this video, we discussed supervised and unsupervised learning algorithms. In the supervised learning algorithm, we have data which is labeled along with the features, and we try to develop the algorithm by mapping the relationship between input features and labeled output. Subsequently, this trained algorithm is employed to predict future observations or future units. Using their features, we try to predict their output labels. In contrast, in the unsupervised learning algorithm, we have only features, not labels, and we try to map or cluster the observations or units together based on similarity in features. And one of the very important and interesting application we saw was that of market segmentation. In this video, we'll discuss the types of data being employed with machine learning algorithms to train and test the models in financial markets and finance domain in general. In general, there are three broad types of data that are employed in finance domain. First is observations about multiple individuals or units collected over a single period. Second, observations about a single individual collected over multiple periods. And lastly, observations about multiple individuals or units collected over various time periods. We'll examine this and visualize these types of data in subsequent discussion. Have a look at this diagram here. We have three cross sections, C1 at time 1, C2 at time T2, and C3 at time T3. Notice, if you collect only one individual, data about one individual like A, over all the three cross sections, that is 1, T1, T2, and T3, then this kind of data is called time series data. You are collecting a time series of information about individual or unit A. In contrast, if you have 6 individuals or more or less individuals like A, B, C, D, E, and F, and you collect all these individuals over a particular time, let's say T1, then it is called cross-sectional data, because you are collecting all the information about these units for a particular time T1. So it is a cross-sectional data. Lastly, if you combine the time series and cross-sectional characteristics, that is, you collect the information about all the units or individual of interest, that is, for example, A, B, C, D, E, and F, not only for one cross-section but all the desired cross-sections like t equal to t1 for time t equal to t2 and time t equal to t3, then this becomes a panel or longitudinal data. That means this panel and longitudinal data comprises or involves the characteristics of time series as well as cross-section. To summarize this video, we discussed three types of data. First, time series data, where we collected information about individual unit over a given time series. Next, we discussed cross-sectional data, where we collected and analyzed data about multiple individuals or units like A, B, C, D, E, F over a particular cross-section of time. And lastly, we discussed panel or longitudinal data, wherein we combined the characteristics of time series and cross-section. We collected the information about all the units or individuals of interest over multiple time periods, and we call this panel or longitudinal data. Panel or longitudinal data. In this video, we'll introduce simple linear regression model. Consider a simple linear regression model the way it is presented here: y equal to beta naught plus beta 1 x plus mu. This is often referred to as two variable linear regression model or bivariate regression model because there are two variables y and x. Y here is the dependent variable or explained or response or predicted or regressant variable, while x here is the independent explanatory, predictor or regressor variable. Notice there is an error term or also called mu, which is error term or residual term or disturbance term. This mu represents the aggregation of those factors that are not explained by y. So in this model we are trying to explain the effect of this part on y. Those factors for which we cannot explain or are not part of this model are aggregated or considered to be part of this error term. These are unobserved factors that reflect variables or factors other than x that affect y. Since mu here is also a random or stochastic variable, it is considered that it has some kind of probabilistic distribution. Often normal distribution is employed to model this error term mu. But the idea here is that this is random in nature and its values assume some kind of probabilistic distribution. Beta naught here is the constant term, while beta 1 is called the slope term. This is so because this relationship, this model, can be represented on a two-dimensional space, xy space, where this model is basically a straight line with this intercept or constant term as beta naught, and the slope of this line is represented as beta 1. So this line represents in visual terms this model. So this is a visualization of this model. This simple model aims to study the dependence of y on x, that means how x affects y. Now please note here that regression deals with the dependence of one variable over another. It does not imply simply causation. The idea is that it only establishes the statistical strength of the relation. The causation has to be established a priori by theory. For example, if instead of y, like this, the dependence on y, you replace an x with y and you put it like this, even then the regression model, the mathematical modeling, will give you some kind of statistical relationship, which obviously may be spurious in nature. Take for example crop and rain. Now a priori we already know that crop affects rain. Rain affects crop. Rain affects crop. This is established by our common understanding, common sense. However, even if you put or replace rain and with crop and you try to find some kind of mathematical relationship from crop to rain, the regression model, the mathematical model, will give you that relationship, which is obviously spurious in nature, and therefore a priori theoretical considerations are needed to imply the causation. Now in regression analysis, the dependent variable, which is y, is considered random or stochastic in nature. That means it assumes some kind of probability distribution. The reason is that it also incorporates the effect of all those unexplained or not considered factors which are aggregated in the error term mu, which was stochastic in nature. So those effects or influences will also be incorporated in y, and therefore y is random or stochastic in nature. In contrast, the explanatory variable, which is x, is assumed to have fixed value. That means it is considered to be coming from outside, while y is part of this model and therefore it is random in nature. X is fixed and taken from outside. So the x values are fixed and taken from outside in the model. A closely associated concept here is of correlation. Correlation here establishes the degree of linear relationship between the two variables, let's say x1 and x2. In correlation analysis, both variables are treated in a similar manner and considered to be random. That means no causality from one to other is implied. Let's take, for example, if variable x1 moves by 1%, then x2 moves by in the same direction by, let's say, 0.5%, then there's a 50% correlation between these two variables. However, we do not imply any causality here. To summarize, in this video, we examined a simple linear regression model, bivariate model, where there are only two variables, the dependent variable y, a constant term, independent variable x, and a slope or coefficient term beta 1, along with the error term. Y here is the dependent variable which reflects the impact of our model, which is beta naught plus beta 1x, while those effects or influences which are not accounted for by this model are considered to be aggregated into this error term. Now please note, by definition of this model, y here is random and stochastic in nature because it also incorporates the effect of these mu or unexplained part of the model. The explained or modeled part, this here, the variable x is considered to be fixed in nature and taken from outside, while y is getting affected by this model itself, which includes the effect of mu, and mu being random stochastic in nature, y is also random and stochastic in nature. This relationship, while it is mathematical in nature and statistical significance is established through mathematics, the theoretical underpinnings or causality from x to y has to be established a priori from theory, not the mathematics. In this video, we'll discuss the role of expectations operator in the context of a random probabilistic variable. Any random probabilistic variable is often represented through expectations operator. This random variable can be the error term or the dependent variable like y. Since these variables attain multiple values, for example, let's take an example of coin tossing game where there are two possible values, and if the coin is fair, then there is a 50% chance or odds for any of the outcome, whether it is head or tail. Similarly, in regression, any random variable like the dependent variable y, if it is assumed to be probabilistic in nature, its expected value is represented as ey. For example, if there are n probabilities that an event has an outcome of y1, y2, y3, yn with possibilities p1, p2, these are probabilities p1, p2 and so on up till pn, then the expectation of this variable y is defined as p1, y1, p2, y2 and so on, that is sigma py. P is probability, y is possible outcome, pi, vi are equal to 1 to n, where n are the possibilities in the event. This is also called probability weighted mean. If all the probabilities are assumed to be equal, that means many times we do not have any a priori knowledge about possible probabilities. So if all the probabilities are assumed to be equal, then p1 equal to pn so on equal to 1 upon n, and in that case the expectations is nothing but the simple average of all the possible outcomes of y's. To summarize, in this video we discussed the role of expectations operator for random probabilistic variables or stochastic variables like error term or dependent variable. We noted that expectations are nothing but simple probability weighted mean of variables. In case we do not have any a priori probability assigned to these outcomes yi's, then in that case the expected value is nothing but simple average of y. In this video, we'll understand the basics of simple linear regression algorithm with a simple example. Consider the table shown here where family income and consumption expenditures are provided. Here, a population of 60 families is divided into 10 income groups, for example, 80, 80 to 100, 100 to 120, and so on up till 260. So there are 10 groups and their consumption, weekly family consumption expenditure, the Y's are also shown. For each level of income X, we try to compute the conditional mean, that is expected Y given X, which is 65. Let us see how this is computed. For example, consider an income level of 80. Corresponding to this income level, a set of family weekly consumption expenditures, that means Y's are provided. So for this given level of X, the corresponding Y's are provided. The summation of these Y's is 325 and their mean is 65. Now this 65 is the conditional mean of Y conditioned upon a given value of X, which is 80, and that is why it is called conditional mean of Y, expected value of Y given X. Recall that in the previous video we said that if we do not have any a priori probabilities of any set of values, we take simple average to compute the expected value, and the same thing we did here by taking the average of these values, which is 65 for X equal to 80. Now the average of all these values is 121.2, and since this value, which is the average of all the values, is not conditioned upon any specific X value, this will be called expected value of Y, which is unconditional mean or unconditional value of Y, because it is not conditioned on any X value, it is unconditioned expected value of Y. Please note that such unconditional value does not account for any income level, that means any value of X, and it is the prediction or expected value of Y or the prediction of Y when there is no knowledge of X. However, one would like to improve upon the value of Y by knowing the value of X if one believes that X affects Y. So if X indeed affects Y, then the knowledge of X would definitely improve the prediction of Y. So if you have the knowledge of X, you can improve your prediction by computing the conditional mean of Y, which is this expected value of Y given X, and that prediction will be more accurate. For example, the conditional mean of Y given X equal to 260 will be 173, which is different from conditional mean of Y when X was 80. Now, if one asks what is the best prediction or mean value of weekly expenditure for an income of X equal to 140, then you would tell him that looking at this table, you will tell him a value of 101. That means the knowledge of income level, that is values of X, enables us to better predict the mean value of consumption. So our prediction of Y, which is the mean, improves as compared to the situation when we do not have that knowledge. So this is the essence of regression modeling. So what we are saying here, that for each level of X, we have set of Y values, and the mean of these Y values are joined together. These means of Y values for each level of X, we have expected value of Y given X, and all these conditional means are joined to get the regression line. So this regression line is nothing but the conditional means conditioned upon these X values are joined together to get this fitted line. So for example, if you have the weekly incomes given on X axis, and for each set of income you have a distribution of Y values, this is the distribution of Y values, and we know that for any distribution, if a variable has a distribution, it is stochastic in nature, we can compute its expected value as we have already seen using the probabilities. We can get the conditional means for each given X. We can compute the expected value of Y, that is expected value of Y for each given Xi, where Xi can be 80, 90, in this case 80, 90 and so on. And once we have those conditional means, we can join them to get the regression line. And then in that case, our estimate of Y would be conditioned upon Xi. For any value of Xi, we can predict the value of Y. To summarize, in this video, we said that any regression model of this type, Y equal to B0 plus B1X, Y equal to B0 plus B1Xi, assumes that some variable Xi has some explanatory power over variable Yi, and therefore one can improve the prediction of Yi, the prediction value of Yi, which is Yi hat, can be improved by using the knowledge of xi. Thus, regression modeling improves the prediction of yi by taking a set of values of xi. For example, if we have the knowledge of xi, the corresponding values of y can be averaged, and this average value of yi for a given I is a better estimate of y. Since this estimate of yi, that is yi bar, is for a given value which is xi, and therefore often such estimate is called conditional mean of yi, that means conditional value of y given x, and this is called conditional mean of y. Another type of expectation of y, which is unconditional mean, which ignores the value of x, which does not consider and assumes that we have no knowledge of x, is expected value of y, which is the average of all the values of y irrespective of values of x. It is often considered, as per regression modeling, that this conditional mean is an improved estimate of y as compared to the estimate of y when we have no knowledge of xi's. In this video, we'll introduce the concept of population and sample regression functions in the context of regression modeling. Recall, in the previous video, we said that if we join the conditional means of y given x, these were the conditional means of y given x. If we join these values, then we obtain what we call is a population regression line. So we join them for each value of xi, x1, x2, x3, and so on. We had a set of values on y, and we joined the mean of these values, what we call conditional mean rather, for given xi. What is the mean of y? When we join these conditional means, what we obtained is called population regression line, which is essentially the regression of y on x. Now, a population regression curve is simply the locus of these conditional means of the dependent variable, which is y, for the fixed or given values of explanatory variable, which is x here. So this is the basic concept of population regression function. The population regression function discussed here can be denoted by this expected value, which we have already seen, expectation of y given xi. This is often referred to as population regression function, fxi. Here fxi is a linear function of x, which is called a population regression function. When we say it's a linear function, this linearity means linearity in parameters, and this can be more simply written as expected value of y given xi equal to beta naught plus beta 1 into xi, where beta naught and beta 1 are population parameters. These are population parameters because they are for the entire population, assuming the population is known, which is a more hypothetical construct. You never have the entire population, but assuming you know the population, then these are the population parameters or the true values of beta naught and beta 1, which reflect the relationship between y and x. Now, when we say this is the linearity in parameters, that means, for example, if this kind of expression is there, where the population regression function is beta naught plus beta 1 square xi, this model is non-linear in parameters and will not be estimated with linear regression modeling that we are discussing here. However, a model like expected value of y given xi, which is equal to beta naught plus beta 1 xi square, this model is, while non-linear in variables, it is linear in parameters beta naught and beta 1. So population parameters are linear, and therefore it can be handled under linear regression models. However, in real life, we do not have the luxury of population. We often work with much smaller set of data, which is called sample. And therefore, what we estimate is not the population regression function, but what we get is the sample regression function. And it is denoted by adding a hat symbol. This hat indicates that we are working with samples. And therefore, the estimated values of y is yi hat. So yi hat is the estimate of population value, which is y. So yi is the population, this yi hat is the estimate of y, which is given with this regression sample regression function, where beta naught hat and beta 1 hat are sample parameters. Unlike the beta naught, which was the population, beta naught and beta 1, which were population parameters, beta naught hat and beta 1 are the sample parameters or the estimators of population parameter, which is beta naught or beta 1. So beta naught here is the estimator of beta naught. We'll discuss some of these estimators. Beta 1 hat is the estimator of beta 1, and these estimators are applied on a given sample to estimate or proxy the population parameters. Using these beta naught hat and beta 1 hat, what we get is yi hat, which is the estimate of y, which is the estimator of population values based on our sample regression function. So SRF, which is the sample regression function, is only an estimate of population regression function based on a given sample or the sample that is available to us. Remember, we do not work with population. We do not have the luxury of population. Now, since this is only an estimate, therefore sample regression function can overestimate or underestimate the population regression function or population regression function values. For example, if you are estimating yi hats and you get this kind of estimators beta naught hat and beta 1 hat, your sample regression function line may look like this. This is one example where actual population regression function is this. So from this point onwards, you overestimate the population values of y, and behind this, below this point a, before that you underestimate the population values. So your estimate is overestimating here, underestimating here. To summarize, in this video, we discussed the concept of population regression function, which was nothing but the values of y using population parameters beta naught plus beta 1 into x. Now, beta naught and beta 1 here are the population parameters. Please note, in real life, we do not have the luxury of working with population, and therefore this is not observed. This is not observed. So the set of population is not observed, and we only try to map this population or estimate using a much smaller sample, which is called sample. So you work with samples in real life through which you try to make estimates or hypothesis or various predictions about the population, which is much larger in size. When you work with sample, you denote this with a hat symbol, y hat. You do not have actual yi's and xi, you have yi hats, which are the predicted values, beta naught hat plus beta 1 hat into xi. Now, please note this yi hat is the prediction of y. This beta naught is the estimator of population parameter, which was beta naught. Beta 1 hat is the estimator of beta 1, which was the population parameter, and this is called SRF, sample regression function, because it is estimated on a sample which is available at hand, and it tries to estimate the population values, population parameters and population yi's. However, please note this yi hat is often not very accurate, and it may over predict or under predict the actual values. In this video, we'll discuss a very important class of estimators called ordinary least square estimators. Recall the sample regression function which we discussed was yi equal to beta naught hat plus beta 1 hat xi plus mu I hat. Here we have removed the hat because now we have also included the error term. Earlier we saw this yi hat equal to beta naught hat plus beta 1 hat into xi, which is nothing but the prediction of yi hat, the predicted value of y hat. Once we add the error term in the prediction, it becomes the actual yi. Now, the error term, this mu I hat, or often also referred to as mu I, is important here, because this error term, which is yi minus yi hat, or yi minus beta naught hat minus beta 1 times beta 1 hat xi, this error term is an important, very important cost function, and any regression fit or any estimator should minimize some function of this error. In this particular case, the OLS, ordinary least square procedure, as the name suggests, tries to minimize the square of this function, and therefore the best cost function to minimize this can be shown as follows. This is the appropriate cost function, which is the sum of squares of error term, which is yi minus yi hat raised to the power 2 summation. This is our cost function, which is minimized here. Now we can also replace this yi hat using this expression here. So we get yi minus beta naught hat minus beta 1 hat into xi raised to the power 2 summation is our sum of squares. Now we minimize these squared residuals. Question is, why not minimize just the residuals or absolute residuals? Now, talking about simple residuals, it fails to recognize the fact that large positive and negative errors, for example plus 6 and minus 6, will tend to cancel each other out. So if there are large deviations, large error terms mu1 I and mu j, which are very large, but on the summation they tend to cancel each other out, Simple summation of residuals will ignore that. Similarly, if we are minimizing the absolute residuals, to an extent that is an improvement because it will recognize that plus 6 and minus 6 or positive and negative residuals should not cancel each other, and therefore large errors, whether positive and negative, they are penalized. However, in case of squared residuals, it penalizes large errors more strongly. So the penalty on large errors is much more stringent in case of squares as compared to simple absolute residuals. To further illustrate and visualize this argument, let's have a look at set of observations plotted on this XY diagram. These are the actual values that we have, rather not population but a sample that we have obtained. Now we try to fit a sample regression function or sample regression, the line corresponding to the sample regression function, which is represented as yi hat equal to beta 1 hat plus beta 2 hat. Now obviously because we are working with samples, these are estimators. Since these are OLS estimators, we try to minimize the sum of these squared residuals. The difference between the actual values and this fitted line, so this is our sample regression function, the line corresponding to sample regression function. This distance is my error in prediction. Now this error, the larger this error, the problematic it is for me, and therefore a function which minimizes the square of these errors gives higher penalty to large errors as compared to small errors. If I would have added simply the absolute residuals, it would have definitely penalized errors, but a square of residuals penalizes large errors much more than simple absolute summation. Now in this scheme, our final function or square residual summation is this, which we can also write as summation of mu I square is a function, obviously a function of beta naught hat and beta 1, because it is written like this. So it must be a function of beta naught hat and beta 1 hat, which are the key parameters or estimators of importance. So these are sample parameters that we are interested in knowing. Now a very regular simple scheme to minimize this, we want to minimize the squared residuals, we can set the differential of this partial differential with respect to our betas equal to 0. We can set this differential with respect to parameters, different parameter estimates beta naught hat and beta 1 hat equal to 0, and then set the condition of the double differential to positive for minima condition to obtain the estimates of beta naught and beta 1 hat, as we will shortly see. And this is the reason why these estimators are called least square estimators, because we minimize the square residuals, and such scheme or regression model obtained from such scheme is also called Gaussian standard or classical linear regression model, by minimizing these least square errors. Now if you recall, we said that mu I square can be written as this function, which is yi minus beta naught hat minus beta 1 hat xi summation, square summation. We can take the partial differential with respect to beta naught, which is, since it is square term, this is minus 2 times this term, which is same, and then differential of beta naught is nothing but a minus sign, so we get this minus 2 times mu I hat. Why? Because this term itself is yi hat, and yi minus yi hat is nothing but mu I hat, or often referred to as mu I itself. The error, we are interchangeably using mu I hat or mu I here. So this is nothing but minus 2 times mu I, which is the partial differential with respect to beta naught hat. Similarly, we can take partial differential with respect to beta 1 hat, which will be very similar, only that now because beta 1 hat has a multiple of xi, we have an extra xi here. So we have minus 2 times mu I hat into xi summation. This is the partial differential with respect to beta 1 hat. Now we need to set these differential equal to 0 and solve the equation. A closed form solution can be obtained, which is shown here. This closed form solution can be obtained only if certain assumptions are met. Now in this lesson, in a set of series of videos, we will discuss some of these assumptions that are needed, and if these assumptions are met, then we can obtain a closed form solution like this. That means we can precisely estimate the values of beta 1 beta naught and beta naught hat. So we can obtain these beta 1 hat and beta naught hat estimators, and these estimators are often referred to as OLS, ordinary least square estimators, because of the minimization of these residual square scheme. These are called ordinary least square estimators, beta naught hat and beta 1 hat, and once applied to a given sample, we obtain the estimates of population parameters. So what the estimates that we obtain, the beta naught hat and beta 1 hat based on these formulas, these are the estimates from the sample. To summarize, in this video, we discussed a very important class of estimators called ordinary least square estimators. The ordinary least square estimators are obtained by minimizing the sum of squares of residuals shown by a formula here. To visualize this scheme, we plotted all the observations from our sample like this. Then we try to fit a line, which we often call the line corresponding to the sample regression function, because we are working with samples. So this sample regression function line can be written as yi hat, because these are only estimate, not the population values, beta 1 hat plus beta 2 hat xi. And then we compute these error terms, that means the difference from these observed values to the predicted values, which is yi minus yi hat. This is the gap, which is called mu I, or we are referring to as mu I hat or mu I interchangeably. And then the square of these mu i's are minimized to obtain the estimators beta 1 hat and beta 2 hat, which are called the OLS estimators.